Hello everyone, in this video lecture we'll be learning about fiber bending losses. So it is one of the factors in attenuation. So what is fiber bending losses? So fiber bending, as from the word, it means if there is any bending of the fiber, there can be some losses. So as you can see in the figure, there is a normal fiber and there is a bended fiber. So when there is a bending of the fiber, there is a change in core radius. So there will be some part of the optical fiber with more radius and some part of the fiber with less radius because of the change in shape of the optical fiber because of the bending. So you can see because of the bending there can be some radiation of the signal which results in loss. So this type of loss that occurs in an optical fiber is called fiber bending loss. So in fiber bending losses, if the bending loss is so high that it can cause some mechanical change in the fiber, such type of losses are permanent losses and which cannot be overcome. A slight change in curvature of the optical fiber can be rectified and can be laid, but big mechanical problems related to the fiber cannot be rectified. And we have two types of fiber bending losses, and first one is macroscopic bending losses and the other one is micro bending losses or mount coupling losses. So macroscopic bending losses, so when there is a bending of a fiber, so there is an associated radius of bending. Okay, so if this radius of bending is more than the radius of core of an optical fiber, then such type of bending is called macroscopic bending. Again, whenever there is a bending of fiber, there is a radius related to that bending. If that radius of bending is more than the radius of the core of an optical fiber, such type of bending loss is called macroscopic bending losses. So you can see from the figure, there is a radius of bending. If that radius of bending is greater than the radius of the core, then this type of bending losses is called macroscopic bending losses. So the next type of bending losses is called microscopic bending. So in microscopic bendings are those losses due to the small bending or the small distortions in the optical fiber. When there is a small bending, that is the radius of bending is less than the radius of core of the optical fiber, such type of bending is called micro bending. So these type of micro bendings can cause small fluctuations in the radius of curvature of the fiber axis, such that the micro bends are created, and due to these micro bends small amount of light is radiated out and there is a loss happening. So the micro bends are mainly due to the manufacturing defect in the cable, that there is a non-uniformity in the core radius, and also when the optical fiber is laid underground, there will be concrete or mud or sand or something like that being laid. If there is any uniformity, if there is no uniformity on the surface that is above the optical fiber, there can be some lateral pressure that is coming onto the fiber. Due to this lateral pressure, there can be small bending in the optical fiber. Because of this small bending, there will be radiation, the signal will be radiating out, hence there will be some losses. So such type of bendings is called microscopic bending, and the losses that arises due to these bendings is called microscopic bending losses or mode coupling losses. Okay, so the next topic is scattering. So scattering is one of the factors that lead to attenuation. So scattering is that word you must be familiar with, why the sky is blue, why we see the color of the sun to be red. The basic principle behind it is scattering. As you all know, the light that is emitted by sun is white light. So white light has 7 colors with pure, in that the lowest wavelength colors being blue and highest wavelength colors being red. So in the principle of scattering, uh, we have a lot of particles inside the atmosphere. So lower wavelength gets scattered by these particles, whereas a higher wavelength particles are not scattered. So the for example, the blue light emitted by sun is being scattered by the particles in the atmosphere. As a result, it get reflected in particular direction. For in our eyes, we see that blue color all over the sky, which is being reflected by a lot of particles that are being present in the atmosphere. Whereas when we look at the sky, at the sun, we see the color of sun as red because it is that light emitted by the sun from the white light, and that light is not uh, affected by the particles in the atmosphere because it has a higher wavelength. Higher wavelength is not affected by the particles in the atmosphere and it is not scattered, so we see the direct red light coming from the sun. So this is the basic principle behind the scattering. So that is the general scattering that happens. Now we have to talk about the scattering that specifically happens in our optical fiber. So whenever, so in general, the scattering occurs due to the particles in the atmosphere. Similarly, the scattering in an optical fiber happens due to the unevenness in the optical fiber. As a result, there is a loss that is happening. So when the optical fiber is being manufactured, there are chances that there can be unevenness, or there can be density fluctuations. As a result, the light rays and that travels through the optical fiber get deviated from its path. As a result, there can be a loss. Basically, when the light is traveling in a particular mode, there is a transfer of energy from one mode to another mode. Okay, our intended mode is one mode. The energy being transferred to the other mode is a leaky mode. As a result, in leaky modes, as we have already learned, the signal gets radiated and lost. So these type of losses that happens in an optical fiber is called scattering losses. So as you can see, it is happening basically because of the concentration concentration of the materials in the fiber, or due to the dopant concentration. So there is a higher dopant concentration in multimode fiber. So scattering losses is more in multimode fiber than in single mode fiber. So the scattering losses can be classified into two types, main categories, that is linear scattering and non-linear scattering. And linear scattering again is this is divided into Rayleigh scattering and Mia scattering, and non-linear scattering is again divided into stimulated Brillouin scattering and stimulated Raman scattering. So linear scattering, as I've already mentioned, when a light is being propagated through an optical fiber, when there is scattering happening, as you all know, there is a transfer of power from one mode to another mode. Okay, we have one intended mode and we have one intended mode. So from our intended mode, the power gets transmitted to another mode. Okay, another mode. So as a result, there is a scattering happening, but there is no change in frequency on the scattering. Okay, so there is no change in frequency. So these type of scattering is called linear scattering. There are two types of linear scattering, Rayleigh scattering and Mia scattering. So next is Rayleigh scattering. Rayleigh scattering comes under the linear scattering. So in linear scattering, there is a scattering happening. So there is a exchange of power from one mode to another mode, but uh, the frequency remains the same. Okay, so that is called linear scattering. In linear scattering, we have Rayleigh scattering. Rayleigh scattering is a basic principle why we see the sky to be blue from the light that is being emitted by the sun, which I've already explained. So in Rayleigh scattering takes place in all direction. So the Rayleigh scattering produces attenuation in light rays, and this attenuation is proportional to 1 by lambda raised to 4, where lambda is the optical wavelength. So from this expression, we can understand that lower wavelengths have higher scattering and higher wavelengths have no scattering. So that is why when the principle of light emitted by the sun was explained, lower wavelengths like the blue blue light gets scattered, and that is being reflected, and we see a blue light for the sky. And the higher wavelength, the red light is not scattered, so we see directly that red light from the sun, hence the sun appear to be red in color. So in optical fiber, we have three windows at the range of 900, 1300 and 1500 nanometer. So all are lower wavelength. So at lower wavelength we have higher chances of scattering. So Rayleigh scattering is dominant in all these wavelengths. The Rayleigh scattering coefficient is denoted by gamma r, and it is given by 8 pi raised to 3 by 3 lambda raised to 4 into n raised to 8 p square beta c uh, TFK, where n is the refractive index of the fiber, p is the average photoelastic coefficient, beta c is isothermal compressibility of fictive temperature, and Tf is fictive temperature or thermal equilibrium temperature. Fictive temperature is nothing but thermal equilibrium temperature. The next type of linear scattering is Mia scattering. So the Mia scattering is caused by hologenetic. Hologenetic is nothing but atoms or modules. Molecules. Atoms or molecules, so which are comparable in size with the guided wavelength. So when the wavelength of the light comes across particles whose size is comparable to that of atoms or molecules, or when it is comparable to the size of the wavelength of the light, then Mia scattering takes place. Mia scattering always takes place in the forward direction. The factors responsible for Mia scattering are the cylindrical structure of the cable is not perfect, imperfection of core and cladding interface, core and cladding refractive index is not uniform throughout the fiber, there are fluctuations in core diameter, and due to the bubble or strain in the fiber. So all of these factors are related to the fabrication of the fiber. So when there is a irregularity or non-uniformity, there can be chances that the light get hit with the atoms or the molecules. So when the size of these obstacles or the particles becomes comparable to that of the wavelength of the light, then Mia scattering takes place. Okay, the next type of scattering is nonlinear scattering. So in nonlinear scattering, when there is a light being propagated through an optical fiber through a mode, there are chances that the signal gets coupled to another mode, or the power get coupled to another leaky mode. So when this transfer happens, there is a change in frequency. So this type, and as a result, there can be radiation loss resulting in the scattering. So this type of scattering is called nonlinear scattering when there is a change in frequency on coupling of the power from one mode to another. So in nonlinear scattering, the scattering can take place in either direction, that is a forward or the backward direction. It produces an optical gain, but there is always a shift in frequency. Since there is a shift in frequency that results in the loss of signal, that is, the signal is being we have a signal of a particular frequency. When it is coupled to another mode, the signal changes to another frequency. As a result, there is a change in frequency. So in turn, the signal is lost and there is attenuation. And we have two types of nonlinear scattering. One is stimulated Brillouin scattering, the other one is stimulated Raman scattering. So next is stimulated brilliant scattering. This comes under nonlinear scattering. So consider the case when a laser light beam is traveling through an optical fiber. So there can be variations in the electric field of these beam. That is, this a laser beam being traveling through an optical fiber. There can be variations of electric field of this particular beam. So this variation in electric field of this beam can produces acoustic vibrations. Okay, acoustic vibrations. Due to this acoustic vibration, the incident photon of acoustic frequency as well as a scattered photon is being produced. Okay, this produces a scattering, and this type of scattering is called stimulated Brillouin scattering. The scattering happening due to the change in electric field. As a result, there can be acoustic vibration. Because of this acoustic vibration, there can be a scattered photon produced as well as with the photon. With the incident photon, there can be an acoustic or scattered photon. Okay, so this can produce a scattering, and this scattering is called Brillouin scattering, and this scattering is usually in opposite direction to that of incoming beam. Okay, this type of nonlinear scattering is stimulated Raman scattering. Stimulated Raman scattering is due to the inelastic scattering of photons. Due to stimulated Raman scattering, there is a spontaneous emission of photons that takes place. Because of the spontaneous emission of photons, there can be a spontaneous scattering. So we have certain photons here. Due to the scattering, the energy of these photons are being transferred to other photons. Okay, so when scattered photons lose their energy, it is called Stokes shift, and when the scattered photons gain energy, it is called anti-Stokes shift. Okay, so if the photons of other frequencies are already present, then the scattering of such photons takes place, and in this case, the two photons are generated, and it is called stimulated Raman scattering. Okay, we have certain amount of photons, and due to this photons, there can be a spontaneous emission of other photons, and due to the scattering, there can be another two photons being generated. So as a result, there is a collective number of photons being there, and between these photons, there is a transfer of energy between near frequencies. As a result, certain scattered photons lose their energy, and certain scattered photons gain energy. As a result, there is a stimulated Raman scattering that is being happening. Okay, so this has the main difference from stimulated Brillouin scattering is that instead of acoustic photons, a high frequency optical photons are being created here. Okay, SRS can occur both in forward as well as in reverse direction.